One of the problems that you have to watch out for when running multiple regression is the perfect multicollinearity problem. Recall that the last least squares assumption for multiple regressions is that there is no perfect multicollinearity. Perfect multicollinearity arises when one of the regressors in the model is a perfect linear function of another regressor in the model. For instance, in model 1, you included the same regressor twice in the same model. And because of this, you can no longer say beta 1 measures the marginal effect of the x variable by holding x variable constant. It doesn't make any sense. And therefore, the interpretation for beta 1 and beta 2 become meaningless. In the second and third model, the regressor z is a linear function of x. And therefore, when you know the value for x and the relationship between x and z, you can perfectly replicate the value for z. In other words, x and z are perfectly related to each other. And because of that, the z variable is redundant when you have already included the x variable in the regression. All three of these models shown here suffer from the perfect multicollinearity problem. If you have taken linear algebra course before this class, you can also think of this problem in terms of the rank of the coefficient matrix. If there is a perfect multicollinearity problem in the model, then the rank of the coefficient matrix will be smaller than the number of regressors in the model. When this happens, we can no longer compute the inverse of the coefficient matrix to find the estimates for betas, because the determinant of the matrix is 0 in this case. This result is shown empirically that R can no longer estimate all the regression coefficients in this model, as you will see in the following examples. In the California schools example, we created 3 variables prior to running these sets of regressions. STR measures the classroom size, test measures the test scores, and native measures the number of native English speakers per 100 students. The variable native is computed using 100 minus the number of English learners in the class per 100 students. In model 1, I tried to use STR and English to explain the variation in the test scores. Then it occurs to me that if I could use English as a variable to explain test scores, I can similarly use the percentage of native speakers to explain the variation in the test scores. So in model 2, I included both English and native in this model. In model 3, I regressed test scores on STR and native. And in model 4, I regressed test scores on STR, English, native, and also coerce the intercept of the regression regression to 0. Let's look at how these regression results differ. Recall that I have included both English and native as regressors in model 2, but the regression output didn't show any estimate for native in model 2. This is a big red flag that I might have the perfect multicollinearity problem in this model. Recall that since English and native are perfectly related, as we know one, if we know one, we know the other, and therefore including both regressors in model 2 make it theoretically impossible for R to estimate the coefficients for both regressors. As a result, R chose to drop one of the variables in order to estimate the coefficients for the rest. However, by forcing the intercept of the model to 0 in model 4, R seems capable of estimating the betas for both variables again. This appears to have solved the problem, but it really have not, because there is no reason why the intercept should be 0 in this case. And therefore, the estimated coefficients for these two variables make no sense. There will be a few situations where you might want to force the intercept of the regression model to be 0, as you will see in the next few slides, but not in this case. In this case, we don't recommend that you set the intercept to 0. This slide summarizes what I had just discussed in the previous slide. You can read this slide on your own. Back to the California schools example. Say now you think the effect of the classroom size by adding one additional student to the class is too small. What really matters is the threshold of the classroom size. More specifically, you believe that if a classroom size has fewer than 12 students, then everyone in the class will receive abundant attention from the teacher, and that will boost their test scores. Otherwise, the classroom will be too big for everyone in the class to receive the needed attention from the teachers, and therefore their test scores will be adversely impacted. Conforming to this view, you construct a small class dummy, which is true if the classroom size is smaller than 12. In the first regression, you regress test scores on the small class dummy and the percentage of English learners. In the second regression, you'll regress test on small class and English, but force the intercept of the regression to 0 by adding -1 at the end of the LM regression. At appearance, these models shouldn't have suffered from the perfect multicollinearity problem, because rationally, the small class dummy and the percentage of English learner in the class should not be perfectly correlated. And therefore, it's not obvious that we will have the perfect multicollinearity problem in these models. But let's see how the regression outputs will show. In the first model, the output shows that R dropped the estimation of the small class dummy, implying that there might be a perfect multicollinearity problem again in this model. On a closer look at the data, we notice that none of the schools in our analysis sample has a classroom size smaller than 12. This means that the small class dummy is equal to 0 for all the schools included in our data set. When this happens, there is 0 variation to the small class dummy. In other words, this dummy variable becomes a constant, which is the same thing as the intercept of the model. In this case, we have the perfect multicollinearity problem between the intercept and the dummy, because the intercept is perfectly collinear with the dummy variable. And that's why R thinks of the small class dummy as the same thing as the intercept and dropped the estimated parameter for this dummy variable. In the second model, we force the intercept of the regression to 0, and therefore you see that the estimated beta for small class dummy is the same as the estimated intercept in the first regression. Because in the absence of an intercept, R is treating the dummy variable that has 0 variation as the intercept of the regression. This slide summarizes what I just said in the previous slide. So far, we have covered 2 different sources of perfect multicollinearity. The first case is when the regressors are perfectly collinear with each other. The second case is when the dummy variable has 0 variance and is hence perfectly collinear with the intercept of the regression. Another possible source for perfect multicollinearity is when all cases of the dummy variables under a broad category are used in the same regression model. This problem is known as the dummy variable trap. Let's look at the wage example again. In this case, I want to examine whether having a college degree can be used to explain the variation in wages. I created a college dummy that is equal to 1 if a person has 16 years or more, have received 16 years of education or more. This subcategory is labeled college yes. Otherwise, the college dummy is equal to 0 or college no. Running the summary statistics shows that if a person has a college degree, then the mean wage is $8.94 per week. A person without a college degree has a mean wage of $5.19 per week. In the first regression, I regressed the wage variable on the college dummy, and because college yes and college no sum up to 100% in our data, and therefore are automatically dropped the estimation for college no due to the perfect multicollinearity problem. The intercept shows what is the mean wage for a person without a college degree. In this case, the mean wage for workers without a college degree is $5.19. The estimate for college yes shows how much more a college grad earns compared to someone without a college degree. In this case, we see that someone with a college degree earns $3.76 more as compared to someone without a college degree. In the second regression, I forced the intercept of the regression to 0 and reran this regression. The output now shows what is the mean wage for each category of workers. For someone with a college degree, the mean wage is $8.95. And for someone without a college degree, the mean wage is $5.19. These numbers correspond to what we have seen in the summary statistics in the previous slide. The difference between showing the mean wages of each category of workers in the regression outputs versus summary statistics is that in the summary statistics, you cannot test the statistical significance of having a college degree, but now you can by dividing the estimated beta by the standard error of this beta. Additionally, when you force the intercept of a regression to 0, when there is a dummy variable trap problem in the model, then we say that this model no longer has a dummy variable trap problem. Because in doing this, you are trying to show the mean wage for each category of workers on purpose by design. This slide summarizes what I just said in the previous slide. Dummy variables do not have to be binary. They can be a categorical variable with multiple levels as well. In this example, I defined 3 dummy variables to describe workers who have not graduated from high school, who have a high school diploma, and who is a college grad. The no high school dummy describes workers who have received less than 12 years of education. The mean wage for workers without a college degree is $4.06 per week. The high school dummy describes workers who have received between 12 years of education, but smaller than 16 years of education. The mean wage for workers in this category is $5.61 per week. The college dummy describes workers who have received a college degree. The mean wage for workers with a college degree is $8.95 per week. If you sum up the percentage of workers in all 3 categories, then you get 100% of workers in the data set. Now, take a note of the mean wage for each category of workers, because you're gonna see these numbers a lot in the following slides. In the first 3 regressions, I regress wage on only 2 out of the 3 dummy variables created to describe the different categories of workers. In the 4th regression, I regress wage on all 3 dummy variables. And in the 5th regression, I do the same thing as the 4th regression, but force the intercept of the regression to 0. Let's see how these regressions pan out. In the first regressions, the estimates are usual. The regression outputs shows the estimates for all the regressors in the model. The intercept for the first regressions show what is the mean wage for the category of workers who are left out in the regression. For instance, in model 1, the intercept shows the mean wage for workers with a college degree is $8.94. And the intercept for model 2 shows what is the mean wage for a worker with a high school diploma. The mean wage is $5.61, and so on. The estimate of negative 3.337 for the high school dummy in model 1 means that on average, workers with a high school degree earn $3.34 less as comparing to someone who has a college degree. And similarly, the estimate of negative 4.891 for the no high school dummy means that on average, workers with no high school degree earn $4.89 less as compared to someone with a college degree. In column 2, the dummy variable that was left out is a high school dummy. And therefore, the estimated intercept shows the mean wage for the worker with a high school degree, and the estimate of 3.337 for the college dummy shows that on average, a worker with a college degree earns $3.34 more as compared to workers with only a high school degree, and so on and so forth. However, notice that the estimate for college dummy in column 4 is dropped. Recall that in model 4, you regressed wage on all 3 dummy variables. And because combining the 3 categories of dummy variables covers 100% of the workers in the dataset, now again you have a perfect multicollinearity problem. And in order to estimate all the coefficients in this model, R chose to drop one of the dummy variables. And because of this, the final estimates of the model 4 resembles the estimates in model 1 when you have included only 2 out of the 3 dummy variables in the regression. In the last model, you coerce the intercept of the regression to 0 when you regress wages on all 3 dummy variables. When this happens, the coefficient estimates show the mean wage for each category of workers. Again, in this case, there is no longer a perfect multicollinearity problem in this model because you created model 5 to get a quick glance on the mean wage of each categories of workers. And you can perform a hypothesis test on each dummy variable to see whether the impact of this dummy on wage is statistically significant. This is one of the very few cases when coercing the intercept of the regression makes sense. This slide summarizes what I just said. You can read this slide on your own.